One last topic to finish off probability, so let's look at conditional probability and independence. So this is a phrase that we've already seen in previous probability questions, and all we want to do today is give it a little bit more of a formal background. So the probability that B happens given A happens is written PB given A. Not much interesting about that. And generally, if we want to find PB given A, that's the fraction of the A outcomes that are also B. So we're saying A's basically happened. What proportion of those are B outcomes? Let's look at an example with some actual words and numbers. This is the information for a school in terms of gender and year breakdown. We want to know the probability that someone is a boy given that they're in year 9. Now that means we want to just look at the year 9s, and there are 67 year 9s, so the bottom of our probability is going to be 67. That's our fraction of A outcomes. What's the probability that they are a boy, given that they are in year 9? Well, that's these 35 boys here. So it's 35 out of 67. That's the fraction of A outcomes, 67, that are also in B, 35. Do the same sort of thing here. Probability that you're a girl, given you're in year 11. Well, there are, again, 67 year 11s, and 41 of them are girls. So it's 41 out of 67. And lastly, what's the probability you're in year 10, given you're a girl? So this, we're going to look at a different total now. So given that we're a girl, there are 108 girls. And the probability you're in year 10, given you're a girl, is 35 out of 108. So it's just a case of looking up the numbers and putting them as fractions of each other. Okay, so one more example of that. We've got a table here of 200 insurance claims. We want to know the probability someone was speeding given it was dry. Well, there were 112 dry days, so this is going to be out of 112, and 21 of those were cases where someone was speeding. 21 out of 112. Fair enough. Next up, we want to know the probability it was wet given someone was speeding. So how many people were speeding? 32. And how many of those days were wet? 11. 11 out of 32. So yeah, if you're told given that, you just need to narrow it down to a certain amount of the situation. Okay, we're going to introduce one more definition here, which is independence, because this is something else you can be asked to sort of test for. A and B are independent if the probability of B and A is equal to the probability of B times the probability of A, and this is something that you do have to go and learn as a general formula. And we're asked here, are the events car was speeding and the weather was wet independent of each other, as in did they affect each other? Now, if they didn't affect each other, if they are independent, this little formula should be true. So what we should do is work out the things there. We should work out probability of B and A. So our B is speeding and our A is was it wet. So we want to know the probability if it was speeding and it was wet, and we want to compare it to the probability of speeding times the probability that it was wet. Now we can get all this information from the table. The probability it was speeding and it was wet is just these 11 things here, so that's 11 out of 200. The probability of speeding is just 32 out of 200, and the probability it was wet is 88 out of 200. And all we need to do is just see, are those the same thing? Now 11 out of 200, let's put these as fractions, is as decimals is 0.055, and speeding times wet is going to give us 0.0704. Those are not the same number as each other, so it is not independent. We can be asked the same sort of questions with a Venn diagram, and again it's just approaching it in the same way. We want to know, in this case, given we've got some cat owners and some dog owners, what is the probability that someone owns a dog? Well, there are 30 people in total in this diagram, and there are 20 dog owners, so it's just 20 out of 30. You could write that as 2/3 if you wanted to simplify it. What's the probability someone owns a dog given that they own a cat? So that means we want to limit ourselves to just the people that own cats. That's 9 people, and 6 people out of those own a dog. So that's also 2/3. Now we want to know, is owning a dog and owning a cat independent of each other? Do they affect each other or not? Well, let's go back to our definition. They are independent if the probability of owning a dog and a cat is equal to the probability of owning a dog times the probability of owning a cat. Now, probability of owning a dog and a cat is these 6 people here, so that's 6 out of 30. And the probability of owning a dog, we work that out as being 2/3. The probability of owning a cat is 9 out of 30. And we end up with this equaling 1/5 and this equaling 1/5. So yes, they are independent. Lastly, we're going to look at one of the classic tree diagram questions where we have, balls in a bag and we take ones out without replacement, which means we don't put them back in. And we're looking to use this to find a given that probability at the end. So let's draw our tree diagram first. You have to take 2 balls out of the bag, so we should have 2 branches going on here. The colours are red and green. And then without replacement, so probabilities are going to change. First ball is 5 out of 8 because there's 5 reds and 3 greens. And then if we picked a red, there would be 4 reds left, so 4 out of 7 and 3 greens. If we picked a green, there would still be 5 reds, but only 2 greens. And let's work out these probabilities at the end here as well. That was 20 out of 56, 15 out of 56, and so on, and so on. And I'm sure those simplify, but let's leave them like that for now. So, actual question, we want to find the probability that the first ball is green, given that the second ball was red. Now, that means we need to narrow it down to situations where the second ball was red. So what's the probability that that happens? Well, that's these 2 branches here. What we need to do is actually add those up to get our bottom probability. That means that we're going to have 35 out of 56 cases are ones where the second ball was red. Now, on the top of that, we want to have what fraction of those cases were just where the first ball was green and the second ball was red, and that's just this one here. So we're going to have our 15 out of 56 there. If we actually do that division, we'll end up with 15 out of 35, or you can simplify that 3/7. So the second question we're asked here is the second ball being red and the first ball being red independent. Now if they were, that would mean that the probability that the second is red and the first is red is equal to the probability that the second is red times the probability that the first is red. And we've worked out lots of this already. So the probability that the second is red and the first is red, that's just this one here, that's just 20 out of 56. The probability that the second is red, we work that out here, that's our 35 out of 56. And the probability that the first one is red, that's just 5/8. So our question is basically, does that work? Now if we simplify those fractions, we'll end up with this side being 5/14 and this side being, I think, 25 over 64 is as simple as it gets. And those are not the same, so we are not independent. Now, I've stuck a little asterisk on this question. That means this is like a genuinely tough question. We're talking grade 8 and 9. Okay, let's look at one last exam question that uses this given that terminology. We're told we've got a number from 1 to 15, and m is the multiples of 3 and f is the factors of 24. We want to fill in our Venn diagram to work out which of these is bigger. So I think the first thing we should do is fill in the Venn diagram. Those are the multiples of 3 between 1 and 15. Factors of 24, so those are things that divide into 24. There's quite a few of those really. I should really be putting these as factor pairs, but well, those are all the ones from 1 to 15. And then 3 is in both of those, 6 is in both of those, and 12 is in both of those. So if we were looking to sort of split this up, we could put 3, 6, and 9, not 9, and 12 in the middle. Other multiples of 3, we've got 9, we've got 15. Other factors of 24, we've got 1, 2, 4, and 8. And then there were some numbers that we didn't use. So 5 would have to go out here, 7 would have to go out here, 8, 9, so 10 would have to go out here, 11, 13, and 14. So we could, if we want, tally up our Venn diagram now and say, well, we've got 2 people here, or 2 numbers here, 3 here, we've got 4 numbers here, and we've got 6 numbers on the outside, and those should add up to 15, and yeah, they do. So let's go to our question. We want to find the probability the number is a multiple of 3 given that it is a factor of 24. Well, how many factors of 24 are there? We found 7 factors of 24. That's the 4 and the 3 put together here. And how many of those were also a multiple of 3? That was, well, 3 of them, so that's 3 sevenths. We're then asked the probability that number is a factor of 24 given it's a multiple of 3. Well, there were 5 multiples of 3, that's the 2 plus the 3 here. And then we want to know the probability that they are also a factor of 24, and there were 3 of those in the middle, so that's 3/5. Now you might not be able to compare fractions easily, so you might want to change them to decimals. That's about 0.42, that's about 0.6. So which of these probabilities is greater? It's going to be the second one.